Good afternoon. My name is Federico, and today I'm going to tell you about our work on communication-aware orbit design for swarms of spacecraft around small solar system bodies. This is a joint work with Satoshi Bandyopadhyay, JP Delacroix, and Amir Rahmani at JPL, and Mark Mote at Georgia Tech. Small solar system bodies are incredibly interesting for planetary science. They are largely not subject to the geological forces that have reshaped larger bodies in the solar system, and therefore they constitute a unique window into the early days of the solar system. In addition, studying small solar system bodies is key for planetary defense, resource utilization, and is a key technology stepping stone on our way back to the Moon and from there to Mars. Because of this, a number of missions to small solar system bodies have been launched in recent years, and here you can see just a few. Typically, these missions have one big spacecraft carrying a bunch of instruments. And the issue with this approach is that different instruments like to be in different orbits. For instance, cameras like to overfly at 9 a.m. or 3 p.m. sun angle, whereas X-ray spectrometers want to fly over at noon when they get as much energy as possible from the surface. And magnetometer may just care about being as close as possible. And satisfying all these requirements results in complex missions with a bunch of orbit changes, as you see here. And at any one point in the mission, only a few of the instruments may be collecting data. To overcome this, we consider an alternative multi-agent concept of operation, where each instrument is carried by a separate spacecraft bus. The instruments are each placed in an orbit that satisfies the instrument requirements. They collect data from the asteroid in parallel, and they can talk to each other, but they can't talk to Earth. They don't have either the power or the large antenna required. To get to the asteroid, the instruments are carried by a carrier spacecraft, which stays respectably away, and the carrier is responsible for coordinating the swarm, collecting the science information from the individual instruments, and relaying it to Earth via the Deep Space Network. Now, the big advantage of a multi-agent concept of operations is that you can have every instrument in its own optimized orbit, you can complete coverage of the asteroid faster, and the failure of a single instrument or a single bus does not mean end of mission. On the other hand, there's a bunch of challenges. First of all, the mission is much more complex and harder to manage. Second, you're dealing with small buses, since they have to fit into the carrier, which poses tight constraints on memories, onboard computation, and communications. And third, I lied when I said that every instrument can be placed in its optimal orbit. You still have to worry about choosing orbits that allow you to not only observe the asteroid, but also make sure that you can relay the data back to the carrier. And this is the subject of today's talk. Our goal is to find a way to efficiently design orbits for this instrument-carrying spacecraft that maximize the science return to the carrier and from there to the DSN over some finite time horizon, accounting both for observation quality and for communication constraints, because we want to get great science and make sure we can get it back. This problem may remind you of constellation design, which has been widely studied in the community. But there is one key difference. If you're designing a constellation around Earth, the orbital dynamics are pretty benign. You can use analytical and semi-analytical solutions, you can write down the effect of J2 and linearize all that sort of things, and none of that is available around a small body, where the dynamics are pretty chaotic, and you have to worry about higher order perturbations. Now, the problem of orbit design around small bodies has been looked at in recent years, but to the best of our knowledge, nobody has studied the effect of the dynamics on the relative pose between multiple orbits, which is critical if you want to understand communication between the spacecraft. So this problem is pretty scary because we don't have all that many analytical handles available. The dynamics are highly irregular and chaotic. We're dealing with observation, which requires us to reason about the geometry of the body, and these bodies tend to look like potatoes. And we have to make decisions like where do I observe and who do I talk to, which are combinatorial decisions. And combinatorial optimization problems are intrinsically scary. So let's try to define our problem and find some structure there. I talked about observation quality, and what we mean in this paper is that we've discretized the surface of the body of interest, and we define an observation function which maps every region on the surface, every time step, and every possible location you could observe the body from to a number between 0 and 1 that says how good that observation would be. And you can think of these as capturing range constraints, sun angle constraints, view angle constraints between the spacecraft and the body. And We won't make many assumptions about this, but we will assume that this function has an analytical form and is differentiable. Think of it as containing some norms and some sigmoids, then maybe some arc cos of dot products. And we also consider a reward function, which just allows scientists to say, oh, this region is more interesting than this other one. We consider a numerical model for orbital dynamics. And the only reason I show this slide is to bring home the point that these dynamics are complex. Your orbits will start drifting after a few revolutions, after a few hours, and you have to account for that in the optimization. Whereas for communications, we consider a simple quadratic bandwidth model where bandwidth goes down with the square of the distance between two spacecraft, a simple obstruction model where we conservatively model the asteroid as two spheres. And if your line of sight is outside the outer sphere, everything is good. If it's inside the inner sphere, you're completely obstructed. And for routing, we assume we have access to delay-tolerant networking, which allows the spacecraft to relay information to each other and store it on board if needed. Now, this problem is still scary, so let's try to do something simpler. Let's freeze the orbits and try to optimize the observations and the communications for given orbits. We start with the observations, and here we pose the problem as an integer program. We define an integer variable O that is 1 if a certain region is observed by a certain spacecraft at a certain discrete time. And we only assign variables to points that the spacecraft can observe according to its pointing capabilities. We try to maximize the reward that we get from observing these points, which also accounts for observation quality. And we have two constraints to make sure that at any one time, a spacecraft is only observing one region, and that over the horizon of the problem, we observe every region at most once, so we don't double dip on the rewards. For communications, we use a network flow model, and I will refer you to the paper for the details, but the intuition I want you to take home is that we connect the spacecraft with a series of pipes, where the area of each pipe is proportional to the bandwidth between the spacecraft at that time step. And we also have pipes between a spacecraft at time t and a spacecraft at the next time step with area proportional to the onboard memory. And the goal of the problem is to push as much flow, push as much information as possible from the spacecraft where the data is collected to the carrier from which we will send it to Earth. Turns out we can write this as a linear program, and we can solve this incredibly fast. We put the two problems together, and we get a mixed integer linear program where in yellow we have the observation problem, and in blue we have the communication problem, which ensures we only get credit for observations if we can get the data back to the carrier. This is a nice mixed integer linear program, or MILP, and we can solve it, but there are two issues with solving this directly. First of all, MILPs can be pretty slow to solve, even on modern computers. And second, MILPs give us no information on how parameters, such as bandwidth, will affect the result. And we would very much like to be able to say, oh, if I change this bandwidth by epsilon, this is the effect of the solution, so we can use that information for orbit optimization. So to get around this, we relax our mixed integer program by transforming our integer constraint into a continuous constraint. And in practice, this has two effects. First of all, we're saying that we can observe a fraction of a region at a given time, and that's okay. Think of it as we observe the full region, and then we throw away the data we can't transmit to the carrier. The second effect is that a spacecraft may observe two regions at once, and that's not okay because we can't slew that fast. So to get around that, we post-process the solution to the LP to ensure that at any one time step, we only keep one direction for a spacecraft to look in. Sometimes relaxations go catastrophically wrong, and to make sure this is not the case, we compare our relaxed solution with a MILP solution for 500 randomly sampled sets of orbits. And we see that typically the relaxed solution is within 5%, and it's rarely beyond 10% from the MILP. So this is not a rigorous analytical result, but it suggests that the relaxation gives us good guidance as the solution to the MILP. Importantly, solving the LP is incredibly fast. We can get a solution in a couple of seconds. And with the LP, we get the sensitivity of the problem to its variables, which will be useful in the following. So at this point, we know how to optimize observations and communications for given orbits. We are ready to turn our attention to the problem of orbit optimization. And your first instinct, certainly our first instinct, was to open MATLAB, search for the global optimization toolbox, and pick your favorite genetic optimization algorithm. But turns out that's a bad idea because the search space is so big. Consider a problem with 7 spacecraft. Every spacecraft has 6 orbital parameters, and if we do a pattern search with just 10 points per parameters, the search space size is 10 to the 42, which is a really big number. We're going to be here a while. So we need something smarter. It would be wonderful if you could compute the gradient of the science returns, the gradient of the goal to our LP, with respect to the initial states of the spacecraft, because then we could follow this gradient and use that to optimize. So let's try to break it out. First of all, the only 2 parameters that depend on the initial spacecraft conditions on the spacecraft orbits in the LP are the bandwidth and the observation quality function. And next, we break out this dependency in a dependency between the bandwidth or the observation quality and the current location of the spacecraft, and the dependency between the current spacecraft locations and their initial conditions. And when we stare at this for a while, we realize something wonderful. We already have a lot of these pieces. Namely, the derivative of the science returns with respect to the bandwidths is one of the duals in the optimization problem. Recall that the duals tell us how sensitive the goal is to some parameters. And if you do the maths, it also turns out the derivative of the science returns with respect to observation quality is just the optimal solution to the LP. So we get these 2 for free. Now, the derivative of the locations with the initial states, that's where all the scary dynamics is hiding, but that's just the state transition matrix that we get for free from numerically integrating the trajectories. And finally, if you use an analytical model for bandwidths and observation quality, you can take the derivative by hand. And it is kind of scary, but we did that for you in the paper, so you don't have to. And for reasonable expressions for bandwidth function, accounting for occlusions and obstructions, and expressions for observation quality that account for range and sun angle and view angle, we can get this gradient at basically 0 numerical cost. Now, the problem still has a bunch of local minima, so you can't just follow the gradient, but we show that following the gradient will often get you 20% to 50% improvements compared to a random start location, so it's definitely worth doing and really cuts down on the number of samples you want to collect to search such a large search space. And now, armed with the gradient, we can propose a simple but effective global optimization algorithm. Sample a bunch of points in the search space, and for each of these points, follow the gradient until you come to a local minimum. And you can do this in parallel. Then return the best point. This is super simple, but it turns out to be surprisingly effective. To see how well this works, we consider a case study with 7 spacecraft orbiting around Eros, a couple of cameras, 2 X-ray spectrometers, 1 imaging spectrometer, 1 altimeter, with reasonable numbers for data bandwidths and a reasonable STM taken from the literature. And we compare our approach with a communication agnostic approach, where first we optimize the science orbits without considering communications. And then once those orbits are frozen, we optimize the communications with our approach. And it turns out that our approach gets about a 10% improvement in the overall reward collected by the system and better quality observations. This is what output looks like. You can see the spacecraft collecting the observations and talking to each other, and the data accumulating on the carrier. It never gets old. These are preliminary results, and there's a lot more we want to do. We want to extend our algorithm to use analytical results on orbits around small bodies to ensure long-term stability beyond the time horizon of interest. We want to capture delta V budget when choosing orbits for the spacecraft. We want to extend our observation model to capture measurements that require multiple spacecraft to operate. Move away from DTN, which is not available on every spacecraft, and also consider simple routing problems. And finally, we are working on a high-fidelity simulator to verify our results by integrating Goddard's 42 orbital dynamics simulator and the NS3 network simulator. And by the way, if you are interested in these results and want to reproduce them, all of our code is open source, and you can find it at github.com/NASA/ICC. With this, thank you for your attention, and if you have any questions, I'll be glad to address them.